Okay, so we're going to start. We're going to continue with chapter 2, but before we do that, I want to go over the steps on how to create a C++ project. And I want everybody's attention on this because we have been having problems on how to set it up because you are missing steps or you just bypass steps. So especially those of you that are having problems, I want you to write it down, make notes, or just go back to this. Okay, so if I'm going to start a project in Visual Studio, the first thing I have to select the project from this start button, Visual Studio 2010. Remember, this is going to be an environment that is going to help us use the editor, use the preprocessor, use the linker, the compiler, and of course is going to execute the instructions that are going to be translated. So once I have this opening window, which is my welcome window, I'm going to select new project. Okay, we just need to wait until it's done. Still opening it up. Okay, here we go. Okay, I want you to make sure that you have Win32 selected. Okay, Win32. Don't go immediately to find the Win32 console application. No, find first Win32 on your left-hand side column, then console application. We're going to give it a name. Remember, this is the name that you're going to be giving to the folder. Make sure that you only use letters, numbers, and underscore. That's it. Do not use any special symbols, okay? Because that will give us an error. So we're going to give it a name. Project, I'm going to say 1 in section 01. We're going to make sure that this create directory for solution is on, and we're going to click on the OK. This is going to open another window, which is going to ask us if we want to go to the next dialog box or we want to finish. We always want to go to the next dialog box. Console application must be selected, and I have to select empty project. By selecting empty project, whatever I had before is going to be erased. Okay. So it's going to be empty project. After I do that, then I finish with this dialog box. This is going to create now the environment for this project. And the next thing that I need to do is create my editor. Again, please do not skip any steps. If we have external dependencies at the end, that means we skip a step or we use a special character for the name. And that is going to bring extra code to our program, and it's not going to run. We're going to get a build error. So we have to be careful with that. It's still loading up. It's coming out now. As you can see, we have the solution project, and then we have project. I have external dependencies, header files, resource files, and my source files. None of these folders have a plus. That means they are empty. I'm going now to right click on project 101. This is where we right click. Not on the source files, not on the resources, not on the header, not on the external dependencies, but on project 1. So I right click. This is going to give me a shortcut menu, and I'm going to select add new item, and we want to make sure that we select code from here again and C++ file. We give it a name. I'm going to use the same name that I use for my folder, project _1 _01, and I'm going to add. And this is going to open my editor. So right here, where it was blue, now I have my editor. I have the tab that is project 101 CPP, which is C++. So now I can start. The first thing that we're going to be doing is our first line is going to be the comment line, always. From now on, in our comment line, we're going to write the description. This is going to be the program description. And I want you to write another line with your name and the date. A third line with the date. So from now on, this is the format that you're going to be using. First line is going to be the program description. Second line is going to be your name. Third line is going to be the date when the project is due. This is how we want. If the program description needs more than one line, then what we do is, again, we open a second line with the double slashes. After this, what is the first line that we need to code for our program? The include. We need to give the directives to the preprocessor. So we always start with pound include. In the angle brackets, we have to use the directive, the name of the file. What directive do we need if we're going to be using a COUT? IO stream. IO stream is the one that we need, right? If we're using COUT. If we're not using COUT, we don't need this. Maybe we need another directive, but not IO stream. Only if we're using COUT. After we list all the directives, how do we close this line? Because this is a line, but it's not the end of the statement. How do we finish this statement now that we started by putting pound include? Using namespace std, right, for standard. So I close it. This is the end of my statement. I started by including a directive that is called IOStream that I'm going to be using in my program because I'm going to be using the COUT object. After this, we can start the main function of my program. So to start the main function of my program, I start with int main, open and close parentheses. Every time that I list a function, I have to use the parentheses, open and the close parentheses. Then inside this function, I'm going to write my code. My code. So like in the program that you were creating with the diamonds, the displaying of the diamond made up of asterisks is going to be here within this curly braces. So your program goes here. And what is the last line that you're going to need if we're going to be ending the program? Return 0, semicolon. So we can say that this is going to be the shell that we're going to use for every program. after we're done, if I don't see any underline, the curly red line in my program, that means syntax-wise is correct. Everything is correct. If I see something with this, let me show you here. Do you see ST, and under ST, do you see the line, the wiggly line, the red one? That indicates what? There's an error. So if I move the cursor, it's going, and I put it over it, it's going to tell me something about that error. Name must be a non-space name. Okay, so ST is not a namespace name. So I can immediately find out what is the problem with it. So I put my D right here. As soon as I put the D, the line disappears. It's gone. The same thing, if I put, instead of the I put an L here. What happens? It's telling me there's an error somewhere, right? I cannot run this program because I still have to debug it. There are syntax errors there. So I go to the include, and it's going to, error cannot open the source file LO stream, and it cannot open it because it doesn't exist. There's no LO stream. There's an IO stream, but not LO stream. Here the standard, it's also giving me an error. This must be something that I understand. And this was created, this error was created because of this line right here. Even though LO stream is not marked, that's where the error is. So sometimes the error is going to be before or after the mark. Okay? So I'm going to correct this, and now I have IO stream. Yes?
On the hashtag include, what if it doesn't turn space gray?
Then there's something wrong. If you're using Visual Studio, Visual Studio is going to guide us by coloring the different keywords or programmer identifiers. Okay. Like in this case, main is not blue, which indicates main is a name that was created by the programmer. STD is a name that was created by the programmer. Everything that is blue is going to be a reserved word for C++ or a keyword. So if this is not blue, then something is wrong. If I put here name spaces, look at what happens. It's black. It's not blue because it's misspelled, right? I have an extra S there. And of course, it's going to give me the line indicating that is incorrect. So I go back, erase my S, and it's going to remove the line indicating that there was an error. Questions on this? No, everybody got the steps? Okay, perfect. So now we can continue with chapter 2. Yes? If you still have the error, when you run it, you have a build error. It can be, again, where you're saving it, the file name. Okay. So we will need to check that. Okay, so we are in chapter 2. And we cover already the parts of the C++ program, and we just reviewed that. The COUT object, you did this program with a diamond. So we know that we need to use a directive in order for the COUT to work, and that directive is called? What is the name of the directive that must be used with the COUT? IO stream. For the COUT, we also use an operator. What is the name of the operator? Output stream operator. Okay, every time that we need to send a piece of data to the screen, we're going to be sending it through that operator. And the operator is the angle brackets, right? It's what we call the less than symbol. And it has to be 2 of them. With the COUT, we also learn how to skip a line to go do a return or a carriage feed or carriage return. What can we use to skip to the next line? And L. Not N1, but it has to be and L. And again, if I'm going to be sending, that is a piece of data. Right? So that is going to be through the operator, to the output stream operator. What else can we use? Backslash and then the N. Will that need an operator? No. The backslash and the N, what it's going to need is going to be that it has to be inside the double quotes, right? Inside the string. So we're going to start with section 2.5, variables, literals, and the assignment operator. A variable. A variable is an area in main memory. Main memory is made up of a grid. This is main memory. So when we have a variable, okay, what we're saying is, first, we're going to be indicating where that piece of data is going to be. So it's going to have like a pointer. It's going to point at the beginning of that space in memory. Then, through the variable, we're going to say how much area of memory we need. The minimum representation or the minimum piece of data that we can use is a byte. Remember the 8 bits? 8-bit signals? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8. Let's suppose that there are lights that are flashing inside. 8 signals, on, off, and off. And they can represent letters, they can represent numbers, they can represent symbols. But sometimes we need more than 1 byte. So if I get 2 bytes, I'm going to have 16 dots, right? 16 signals. If I need more, well, I just grab it. So when I'm creating my variable, I'm going to say where it starts and how much area I'm going to be using. And the amount of memory space that I'm using is going to say if it's going to be a number and how big it is. If it's going to be a letter or it's going to be a list of letters. So the variable itself is going to give not only the location in memory, but also the length and the value. And how is this going to be done? Because we're going to be giving a data type and the variable name. The variable name is going to be the pointer. And the data type is going to say what we're going to be storing and the value. Those 2 things through the data type. One of the requirements that C++ has is that before we can use it, we have to declare it. That means we have to introduce it. Let's suppose that I want to work with this pointer right here. And remember, the name is the pointer. So I call this age. That is going to be my pointer. So I want to put it in one of the statements of my program that is within my curly braces. I have age. It's assigned the value of 18. When the CPU tries to put an 18 inside age, it's going to say, hey, wait, I don't know what age is or where age is supposed to have. So I'm confused. You need to give me information about age before you use it. So before we use it, we need to define it. So we have definition, where we're going to be putting a data type and a variable name, and then we use it. I already explained this. Variables, they're very unique because they can change throughout the execution of the program. So at the beginning, I can put an 18, but then I can change it to a 17, and then I can change it to a 16. The only thing is that the variables are not going to keep track of what was there before. They only remember the last thing that they have in that memory location. So there's no history of what it had before. Here's an example. And this is the correct sample because I have the declaration, and here it is. I'm defining it. I'm defining age. So now what I'm with this line right here, what happens is, again, in main memory, age is going to be pointing right here. And because I have this code, int, is going to say, okay, you have 1, 2, 3, 4 bytes. So you have 8 signals, 8 signals, 8 signals, and 8 signals. 32 signals that are going to be making up age. So then I have put a 17 in age. So it's going to have a 17 is going to be probably a 1. And then 2 is off, 4 is off, 8 is off, 16 is on, and then the rest are going to be zeros. So this is the way that it's going to be represented. And it's correct because now age exists. Age has already a place, an area in main memory. Why? Because we defined it right here. Next line is COUT age. So this is going to be displaying it age. Remember, it's a pointer. It goes to memory, and it's going to grab how much? An int. So it's going to grab this area, the 4 different bytes, grab them, and it's going to display it because I have the COUT. So it's going to display the 17. Next line, we have now put an 18 in age. So now this one is going to change. This is going to be now 0, 1, 0, 0, 1, and then the rest are going to be zeros. Where? Exactly in here. So with the next line, what is it going to do, Javier? This line right here. This is where we are. What is it going to do?
It's going to display the age that you put in there.
What did we put in there? What do we have? 18. So that's what it's going to be displaying because that's what we have in there. This value right here. So we started with the 17 and now we have an 18. What happened to the 17? It was deleted. It was replaced. Will it remember that it had a 17 before? No. It doesn't keep history again. We already know how the assignment operator works. Everything that we have on the right-hand side is going to be moving to the left-hand side. And on the left-hand side, the only thing that we can have is a variable name. The only thing that we can have is a variable name. So let's keep that in mind. Okay, another thing that we have in C++ besides variables is constants. Constants, they don't change. The 17 in my program right here is always going to be a 17. Age changed from a 17 to an 18, but the number 17 didn't change. The number 18 didn't change. And we have different types of constants. I'm going to start from the bottom to the top. The first constant that we have is called a floating point constant, which is used to represent real numbers. So we use the digits, we use the decimal point, and we can also use the plus or the minus sign. Then we can also represent the numbers, whole numbers, which we call integer constants. It's going to be just the digits, not the decimal point. If you tell me 12 is the same as 12 dot, that is incorrect. That is incorrect. And we're going to see that because when we are representing whole numbers, we can represent them in one area of memory, and the floating point numbers are going to be representing using another area of memory. So this is not the same. Even if I put a 0 there, that's not the same. Okay, a 12 without the decimal point is an integer. 12.0 is going to be a floating point. So it also can be a positive or negative. Then we have the word hello, and it's going to be in double quotes. Whenever we have more than one character, we call that a string. So if I put A, B, C, it has to be in double quotes. If I put A by itself, it can be in single quotes because it's a character. Single quotes, what happens is going to reserve only one byte. When the CPU finds double quotes, it's going to be reserving 1, 2, 3 bytes. 1 byte per character. So it's going to be the area that is going to reserve in memory is going to be different. So again, this makes a big difference. So if I ask you, what are the types of constants that we can have? We can have a character constant, a string constant, an integer constant, and a floating point constant. There are 4. We already talked about identifiers. We're going to be using identifiers to identify variables, and later on we're going to be using identifiers to identify or to name constants as well. And we already know the rules. We can use letters, numbers, and the special symbol is going to be the underscore. We can start the name with a letter or with the underscore, but never with a number. And we talk about this in chapter 1, but they just review this. We can use the camel format by capitalizing all by the first letter of the first word, like in this one, quantity on order, total sales, or we can use the underscore to separate the words. Questions? Okay, when we're talking about data types, integers, if I give you this 12 and 12.0, which one is an integer, 1 or 2? 1. 1 is going to be an integer. 2.0 is not an integer. So remember, again, an integer refers to a whole number. Okay, it can be signed or unsigned. So we can put 12 with a plus sign or 12 without a plus sign. This is the same. This is going to be the same. When we are specifying, when we're specifying the integers, we have 3 different integers that we can identify. We call the first one a short, the second one an INT, and the last one is the long. And they are, the size is going to be based on the number of bytes. The number of bytes that are going to be reserved. How many bits do we have in each byte? 8. So if I have 8 bits, what is the maximum number that I can represent in here? It's 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. If I add all this, what is the number? 255, 256. Are you sure? Add it. 128, 128, 64, 32, 16, 8, 4, 2, and 1. Yes, everybody? Add it again. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. $255. If all the bits are on, this is going to represent a 255. Yes, everybody with that? This is very important that we understand. Okay, so if I'm going to use a short INT, okay, a short INT, I'm going to create a number that is unsigned. I'm not going to be using any signs. That is from 0 to 65,532. Why? Because I'm going to be using 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. How many bytes am I using? 2. I can also represent a sign. If it's a sign short, I'm still using the same 8 bits per byte, and I'm using 2 bytes. But now I'm going to leave the last one so that I can select the sign. On for positive, off for negative. So instead of having 16 bits, how many do I have? 15. So the maximum number that I can represent with 15 bits is going to be 32,768. When it's off, it's going to be negative. When it's on, it's going to be positive. But it's exactly the same number. So when I have a short integer, okay, this is going to be using how many bytes in main memory? 2. Everybody with me so far? Okay. If I move to an INT, if I say, okay, my integer age is going to be INT, like I did here in this program. Where is it? Right here, age. I put INT, age. I'm saying, remember with the data type, I'm saying the what and how the values, right? What area in memory I'm going to be using and the value that I'm going to be putting in there. So if I'm going to be using an INT, then I'm going to be using how many bytes? 4 bytes. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have, how many bits are on? 32 bits on. What is the number that I can represent? The biggest number that I can represent. 4,294,967,295. Because I'm using that much area in main memory. So if they are off, if I have 0, 0, 0, 0, 0, 0, I have a 0. But if all of them are on, I have 4,294,967,295. Yes, everybody with me? Okay. If I'm going to be putting a sign int, then I lose 1, right? I lose 1 bit that is going to be on and off, representing not the value now, but the sign. On is going to be positive, off is going to be negative. So I lose this one. So how many bits do I have now? 31, because I'm losing 1. I need that for the sign. So I have 31 bits. So my number reduces. What is the maximum number that I can represent? Read it. I don't hear anything. Exactly, 2,147,483,647. It's like half of it, because they can be all on, and this can be on as well, and it's going to be a positive 147,483,647. But if this one is off, then I'm representing a negative 147,483,648. So is it important when we give the data type, what data type we're specifying in C++? Yes, because it's going to be reserving that much memory. So when we create a variable and we put int, we need to make sure that this is represent, the maximum number that we can represent is going to be this, because I don't have a sign. If I put sign, the word sign int, then it's going to be less than that, than the 4 billion. We have one more. In the ints, we have long. Long is going to be different for operating systems, for different operating systems. In ours, is going to be exactly the same. A long is going to be 4 bytes, just like the int. But in some other operating systems, it's twice as much. So instead of 4 bytes, it's going to be 8 bytes. So you can imagine the figure that we can hold in there. Questions about ints? So how many different types of ints do we have? Okay, 6 with sign and unsigned, right? Short, sign, short, unsigned. Int sign, int unsigned. Long sign, long, and long unsigned. So there are 6. Do I have a difference between a short and an int in the size of storage? Short and int. Yes. Int and long? Now it depends on the system. Here's the explanation about the sign. C++ allocates 1 bit for the sign of the number. The rest of the bits are for data. If your program never needs a negative numbers, you can declare variables to be unsigned. The variable is always signed unless the unsigned keyword is used. So it's always going to be signed by default. Okay, the next one, it's when we're declaring integer constants. When we're declaring integer constant, we can also do 2 types of constants that we don't have listed here. And this I'm just going to mention so that you know that they exist. Okay, we have the decimal base. It goes from 0 to 9, and that's what we use, right? The decimal system. We create numbers based with those digits. When we do the binary system, we use numbers from 0 to 1. There are 2 more systems. One of them is called an octal system, and we can write numbers in this base. For C++, when we're using this type of numbers, we have to start with a 0, always. So this 0.75 in decimal representation is going to be 61. It's not a 75. It's not a decimal 75. It's a 61. Just like when I put 1 1 0 0 0 0 0. This is not an 11, right? What is it? It's a 3. The same thing here. This 75 is not a value of 75 in our decimal system, but it's a 61. And what we do is we put 8 to the 0 power, 8 to the first power. And we do exactly the same operations that we do for the binary. You don't have to worry about it. I just want you to know that we can also represent numbers in octal base. We have another base, which is 16. 16, we call them hexadecimal numbers. If we need to represent a number in hexadecimal base, or base 16, then we need to start the number with the 0x. This number, what it really is 10 times 1 plus 5 times 16 plus 7 times 32. That's what the number is. So it's not really a 758. This is a hexadecimal number in 0x758. So just so that you're aware that we have those constants. So we can represent constants in the regular format, decimal base, but we can also represent constants, integer constant with the octal or with the hexadecimal. Okay. Questions? The next type of numbers is the floating point numbers. Floating point numbers are designed to hold real numbers. So that means we're going to have the integer portion of the number, we're going to have a decimal point, and we're going to have a fraction. We're going to have the decimal portion of the number. And that is making a floating point number. So the data type, we have to specify, just like when it's a whole number, we have short, we have int, and we have long. The same thing, we can also have 3 types in the floating point. They are called float, double, and long double. When we're using this type of numbers, they are all signed. So we don't have the option here of saying unsign it or sign it. They will always be signed. And here we have how much area is going to be using of memory. The float is going to be using 4 bytes. 4 bytes. But the number of decimal positions are going to be only 7. So I can only put like 1, 2, 3, 4, 5, 6, 7 decimals. 7 decimal positions. For double, now is going to be using 8 bytes. So it's going to be using 8 bits, plus 8 bits, plus 8 bits, plus 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. How many bits are we going to be using for a double? 64 bits. 64 bits, 64 signals. So that big piece of memory space is going to be used. This one is going to have 15 decimal positions. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6. This many decimal positions. So it's going to be a very precise value. Very precise value. If I'm going to be working with dollars and cents, well, I just need 2, right? 2 decimal positions. That's it. But sometimes we need to enlarge that number of decimal positions because we're working with substances, with quantities like ounces, and we need the measurement to be very precise. So we need that. Long double, again, this is going to depend on the operating system. Ours is going to be 8 bytes. So the number that is represented here, this is in exponent formation. This is 3.4. E means 10 raised times 10 raised to the 38 power. So you can figure that out, how big that value is going to be. The double is less in value, but because of the 15 digits that we have in the decimal positions. There we go. Right here. That's where we are, right? No, I went back to this one. Okay, I gave you this information. It's in your PowerPoint presentation, but you will find it in your book as well. When we're working with floating point constants, we can represent our numbers in decimal notation, just like the normal numbers, or we can also represent it in exponent notation. Remember, the E means times 10 raised to the power of 1. This is times E, which is the exponent, is times 10 raised to the negative 5. So it's going to be less decimal positions, right? We can also force the number to be a floating number or a long number. And this is so that we can reserve less or more area in memory by using a capital F or a capital L at the end of the number. Questions? Okay, what happens if I create a variable and I say int, let's suppose that this is my variable right here, and rainfall. What am I saying with the int? That is an integer, which means what? It's a whole number. Whole numbers, do they have decimals? No. What else am I saying with the INT? How much bytes or how much area in memory am I reserving? Sure? 4? Everybody agrees with that? Let's go back. How many? 4 bytes. So what we're doing with that line, as soon as the control unit reads this line, already converted to machine language and all that, what it's going to do, we have our memory, remember? So it's going to say, okay, rainfall, remember it's the pointer, is pointing right here, and I'm going to be reserving 4 bytes. 1, 2, 3, 4. Right here, this area. But I'm starting right here. And what am I going to be putting in there? 3.88. What happens? It cuts off the decimal portion of the number because there is no space for that decimal portion. It's going to say, oh, it's a 3. So I'm going to put, how do I represent a 3? In binary. 1 and 2, we don't have a 2. 1, 1, 1, 1, and then zeros. How many zeros am I going to have? It uses how many bytes? 4. So how many zeros am I going to have? 30 bits that are going to be off. 0, 0, 0, 0. So that big area is going to have one on signal, 1 on signal, and then 30 off signals. What happens to the 88? Gone forever. It's going to truncate it because we have an INT. We're saying this is an INT, so remember, that name is saying a lot. It's saying how much area and what type of values we're going to be placing in there. And the name rainforest is just, rainfall is going to be a pointer at the beginning of that big area. So when I say COUT rainfall, this again is going to be pointing at that. It remembers that it's an INT, so it brings 8 bits, and 8 bits are going to have the value of a 3, not 3.88. Questions? No questions? Okay, I'm going to stop right here so that I can check your projects, those of you that are still working on it, the diamond. But remember that this is in your e-text. This is chapter 2. The same numbers that we have here, they refer 2.5, 2.4, 2.6, 2.1. They refer to the sections where this, you can read more about this topic. I'm going to ask you to read the text, and then if you have any questions, write them down so that we can go over them next period. And we will continue with 2.9.